Hello class. So on this video, we'll continue on our discussion of system of linear ODEs. In the previous video, we introduced the notation that we're going to be using. Right, so in general, our system of linear ODEs is going to look like this. If it's nth order, it means that there are n derivatives. And again, we're only looking at first order equations, meaning that each equation is first order. Okay? And that's the only time I'm really going to write things. So I will write things like this again, but for the most part, I'll just use the vector or matrix notation that we have here, where we define this matrix, x of t, as just having each of the dependent variables in it. Right. The matrix A having each of the coefficient functions that showed up in the equations here. And then the vector G having the G sub i's that show up in each of the equations. And then we can write our system in this shorthand notation. So let's see an example. Right? So consider the systems. dx dt equals 3x plus 4y. dy dt equals 5x minus 7y. So there's two of them, but let me just start with this one. So let's just focus on this first system. Okay? So we have two dependent variables and two derivatives. Now notice that each equation is first order. Right? Why? Because there's only a first derivative appearing. Right? And each equation is homogeneous, right? Because the g sub i's are 0. Right? There is nothing that is not being multiplied by a dependent variable or derivatives of the dependent variables. Right? So this here is a second order system of first order linear ODEs. If we want to write it in matrix form, then our x would be the vector containing, so let me use a different color. X would be the vector containing the dependent variables, which in this case are x and y. A is going to be the matrix containing the coefficients. Right? And then when I'm just using x and y, always order x first and y first. If I'm using x1, x2, x3, etc., then just order them by subscript. Right? So x1 is first, x2 is second, etc. In this case, when we're just using x, y, and z as subscripts, always write x first, y first, and z first. X first, y second, and z third. Okay? So in this case, what's our matrix? Well, let's look at the coefficients. Right? The first row corresponds to the coefficients of the variables. So it's going to be 3, 4. The second row corresponds to the coefficients in the second equation of the dependent variables, which are 5 and negative 7. Okay. Finally, x prime is going to be just the same as x, but with the derivatives of the dependent variables, which means that we can write this first system as x prime equals a times x. And I will explain why this is the same, why this is the same thing as writing it as equations in the next slide. But for now, let's just practice writing it like this. Okay. So again, notice it's a homogeneous system, right? Because all of the g sub i's are 0, so it matches system 3 here. Now let's do the other one. In this case, we have 3 dependent variables, x, y, and z, and 3 derivatives, x prime, y prime, and z prime, which implies that this one, the second one, is the second system is a third order system, right? Because there are 3 equations of, again, first order linear ODEs. Now let's try to write it in matrix form. So our matrix, our vector x, again, just contains the dependent variables, in this case, x, y, and z. The matrix A contains the coefficients of the dependent variables in each equation, except for the t's, right? The t's here correspond for the g sub i's, right? So anything that is not being multiplied by a dependent variable or its derivatives is just the g sub i's, right? So that's going to correspond to the vector g. But in this case, again, notice that I've ordered my dependent variables in each equation as x first, y first, and then z. Okay? So just write your matrix by reading the coefficients row by row. Okay, so the first row has 6 as the coefficient for x, 0 for the coefficient of y. Right, so anytime you don't see a variable, you can think of the variable 0 times y in there. Right, so there's a 0, and then a 1 in front of z. Okay, so the first row is going to be 6, 0, 1. Okay. The second row, just look at the second equation, look at the coefficients. We have 2, negative 3, and 2. So 2, negative 3, and 2. Then the last row, we have 0x plus 4y plus 0z. Right, so 0, 4z. Oh, sorry, not c. 0, because it's 0 times c. Now, in this case, this system is not homogeneous because there are functions not being multiplied by dependent variables. Right, so we will have, in this case, a vector g. Right? So let's see what it is. So the function not being multiplied by any dependent variables in the first equation is just the function t. Right? So g sub 1 is t. In the second equation, we have the function 6t. In the third equation, we have, again, we have a function of t, but you can think of it as just being the 0 function. Right? You can think of it as being a 0 times t. Okay. So 0 times t is just 0. Right? So just write 0. So you can think of it as 0 times t or just plus 0. Right? Either way. I think actually it's just easier to think of it as there is a plus 0 and not worry about putting in an extra t. Again, our x prime is just the vector with derivatives of the entries in x. So we're going to have x prime, y prime, z prime. And all of these derivatives are with respect to t. Right? T is always the independent variable. So putting it all together, we can rewrite this system as x prime equals ax plus g, where a, x, and g and x prime are given as we wrote them here, right? And the same here, x, a, and x prime are given as we wrote them here. So why is this important? First of all, it gives us a shorthand way to write systems of equations. Second, notice that we're working with linear equations. Again, remember that what was, for all of the theorems we saw in terms of finding solutions of linear equations, linear differential equations, what mattered was not the order, right, or anything else. Really what mattered was the fact that they were linear, because we were using linear algebra. So the fact that all of these equations are linear is going to allow us to use linear algebra. Not only that, a lot of the work we're going to do to solve these systems of equations, and I'll define what a solution is in a moment, is going to be involving just multiplication of matrices. So a lot of things you will learn in linear algebra when you take it, or that you will see in more advanced classes, because a lot of things you do, even in a lot of numerical approximations, like we did an example of numerical approximation with Euler's method, a lot of numerical approximations you use is going to be dependent on linear algebra. So you're always going to see matrices show up. So another reason why it is useful to write our systems in terms of matrices, because it allows us to use the techniques of linear algebra. And again, we can do this because our equations are first order linear ODEs. Now, since we can only work with matrices by hand, with 2x2 matrices, we can do it with 3x3s, but the determinant formula gets a little bit more complicated. So I'm just going to work with 2x2 matrices. I am going to define some operations. The determinant I won't define again. Well, okay, I will define again, just as a reminder, but we've seen before. Now, if you're working in other classes and you have matrices that are larger than 2x2, you can just use Mathematica. You can use Mathematica to multiply matrices, add matrices, multiply matrices by constants, and calculate determinants. So all that you can do with Mathematica. In the 2x2 case, you can do it by hand. So that's what we're going to do in this class, just doing it by hand. So some important operations. The first one is, how do you add matrices? So let's say I want to add matrices A and B. First of all, you can only add matrices that have the same dimension. Meaning that the number of rows in A has to be equal to the number of rows in B. The number of columns in A has to be equal to the number of columns in B. So number of rows in A has to be equal to the number of rows in B. And then the same for columns, right? The number of columns in A has to be equal to the number of columns in, oops. Yeah, no, this is great. Number of columns in A has to be equal to the number of columns in B. That's what it means for the matrices to have the same dimension. Okay? For example, we could add the matrices 1, 2, 3, 4 plus, I don't know, 2, 2, 1, 1. Notice that both of these matrices have 2 rows and 2 columns, so we can add them. How do you add matrices? You just add entry by entry. Okay? So for example, the first entry, we're going to add this and this. So it's going to be 1 plus 2. The second entry is going to be 2 plus 2. So 2 plus 2. Next entry is going to be 3 plus 1. Last entry is going to be 4 by 1. Right, so adding matrices is very easy. You just have to verify that they have the same dimension. If they do, you just add them entry-wise. And notice that the dimension of the resulting matrix has the same dimension as the original matrix, as the original 2 matrices. So let me make a note of that, because it's not going to be the same with multiplication, always. The resulting matrix has the same dimension as the original matrices. And it's the same thing if we're adding vectors. Like, as long as they have the same dimension, we can add them. So for example, we could add the vectors 3 and 4 plus 1 and 2. They both have 2 rows and 1 column, so we can add them. And again, just add entry-wise. So add the first entries and add the second entries. Okay, so you just add entries, just add matrices by adding entry-wise. Now, more generally, you have this formula, which you don't have to use, but just it's a way to write matrix addition in a more general sense. Right? If we want to add matrices A and B, where again, I use this subscript notation where the first subscript is telling you the row, and the second subscript is telling you the column. Right, so notice A11 is because it's in the first row, first column. A12 has those subscripts because it's in the first row, second column, etc. And then we have, let's say, B11, oops, B12, B21, B22, right? And again, notice that the subscripts match, right? The B sub 21 matches because it's in the second row, first column, and B sub 22 matches because it's in the second row, second column. So you just add entry-wise. Right? So this is going to be the matrix A11 plus B11, A12 plus B12, A21 plus B21, and A22 plus B22. So this is the most general way in which you can write it. And it's useful to get used to using this notation where the first subscript means the row, second subscript means the column, because a lot of things you can simplify by just writing them in matrix notation, or just by assigning subscripts like this, so things are easier to read. Now, we can't add a matrix, a 2 by 2 matrix in a vector because they don't have the same dimension. Right? So we can't add something like 1, 2, 3, 4, and 5, 6, because they don't have the same dimension. They don't have the same number as columns. Right? The first matrix has 2 columns. The second matrix has only 1 column. So in this case, we can't add them. Okay? So that's matrix addition. Very straightforward. Now, we also have to define matrix multiplication. However, we're just going to define it in the case when we're multiplying a 2 by 2 matrix by a 2 by 1 vector. Okay. So what if we want to find something like this? Multiply a times, let's say, x, where x is a vector and a is 2 by 2. And again, we're only going to do this by hand in the 2 by 2 case, right? And x is 2 by 1. Right? So how do we calculate this product? Okay. Well, there's the formula. So I'm going to do it first in general sense with the formula, and then I'm going to do it with specific numbers, and you'll see that it's very easy to do. Okay. So if A is given by, again, A11, A12, A21, and A22, and x is given by, let's just say, x1, x2, right? Then, by definition, so I'm just giving you how this works, ax, this product, is given by, well, it's going to look like a11 times x1 plus a12 times x2. That's going to be the first entry. And then the second entry is going to be a21x1 plus a22x2. So notice this is a 2 times 1 matrix. So we started with a 2 by 2 and a 2 by 1 matrix. After multiplying them together, we end with a 2 by 1 matrix. Now, in terms of multiplying matrices in columns, you can't always do it. The condition is, for multiplying like this, is that the number of columns in A must equal the number of rows in X for the multiplication AX to be defined. So notice that in this case it works because A has 2 columns, which equals the number of rows in X. So this matrix multiplication is justified, it's defined, and it's calculated like this. Now, it's easier to see what's going on if we use specific numbers. So let's do an example. Let's say you want to multiply or find the product 1, 2, 3, 1 times 1, 1. And again, notice that the number of rows of columns in the first matrix equals the number of rows in the vector. So how do you calculate this? It's going to be a 2 by 1, and it's calculated like this. The first entry, you multiply this entry in first row with this entry in X. Right, so it's going to be the first part of the first part. So it's going to become, let me use a different color, make this red. So it's going to be 1 times 1 plus, what's the other part? Well, now let me use blue for another color. Now you're going to take, again in the first row, take the second entry and multiply times the second entry in X. Right, so we're going to have 2 times 1. And do the same thing for the second row. Okay? So for the second row of A, take the first entry, multiply by the first entry in X. So it's going to give you a 3 times 1. And then for the second entry, multiply the second entry in the second row with the second entry in the X vector. So this ends up being 1 plus 2 is 3, 3 plus 1 is 4. And that's the idea. Work with one row at a time. So start with row 1, multiply the first entry in row 1 by the first entry in X, second entry in row 1 by the second entry in X, and add them. And that's the first entry of your resulting matrix. Then go to the second row. Multiply the first entry in the second row times the first entry in X, and then add the product of the second row of the second entry in row 2 by the second entry in X. Now, this is the most complicated part. The addition is very straightforward. So let's do one more example. Say we want to do let's make it a little bit bigger. So 0 times 4 times negative 1, 3, and then we want to multiply this just more generally by some variables, x1, x2. So what is this going to equal? So start working with the first row. Multiply the first entry in the first row by the first entry in the vector x. First entry in the first row is 0. First entry in the vector x is x1. Then add what? Well, you're going to add the product of the second entry in row 1 times the second entry in x. So a second entry in row 1 is 4. Second entry in x is the variable x2. And that's the first entry in the resulting matrix. Now go to the second row. Okay. Multiply the first entry in the second row by the first entry in the vector x. First entry in the second row is negative 1. First entry in x is x sub 1, sorry. And then you're going to add. Okay. Now go to the second entry in the second row, which is 3, and multiply by the second entry in x, which is x sub 2. So this is the best way to think of it. So you don't have to memorize this formula I gave you above. You just have to memorize, okay, I do it row by row. So when we simplify this, we get 4x2 and then negative x1 plus 3x2. And again, we get a 2 by 1 matrix. So these are the two operations that we need to be comfortable with: adding matrices and multiplying a matrix and a vector. And then, of course, the final thing is the determinant of a matrix. So determinant of the matrix, again, just doing 2 by 2 matrices. Remember, this has a very simple formula. First of all, notation-wise, it's the same as just writing the matrix in with vertical lines instead of brackets. And the formula, the formula, if you remember, was very straightforward in the 2 by 2 case. Just multiply the first diagonal, right, so AD. So let me do that in a different color. So do AD. And then subtract the product of the entries in the other diagonal. So times minus B times C. And these are the three operations we're going to need for us to be able to find solutions to systems of ODEs. So as summarizing, matrix addition, you have to have both matrices have the same dimensions, meaning the same number of rows and the same number of columns as each other. And then you just add entry-wise. You can add matrices, you can add vectors because they're also matrices. Okay. And then for matrix vector multiplication, the number of columns in your matrix has to be equal to the number of rows in your vector. If that's the case, the product AX is always defined. It's defined like this, as this formula. If you just want to do it by hand without memorizing, just work row by row, okay, as we did in this example. And then finally, the determinant, which we already learned how to do before.